In this video, I will explain the squeeze theorem in a simple and straightforward way, and we'll work through some examples to help you understand. Let's imagine three brothers, each represented by a different color. Suppose the height of the first brother on the right is greater than or equal to the height of the second brother, and the second brother is taller than or equal to the third brother. In other words, the younger brother can be as tall as his older brothers, but not taller. As time goes by, let's say the height of the first brother becomes 2 meters, and the height of the third brother also becomes 2 meters. Now, what would be the height of the middle brother? The middle brother, like a sandwich, must be shorter than or equal to the first brother, and taller than or equal to the third brother. If both the first and the third brothers are now 2 meters tall, then the middle brother has no choice but to be 2 meters tall as well. Now, based on this analogy, let's explain the squeeze theorem. If f of x is greater than or equal to h of x, and less than or equal to g of x for all x in an open interval containing c, except possibly at c itself. Here, h of x represents the youngest brother, f of x represents the middle brother, and g of x represents the eldest brother. As x approaches c, if the limit of h of x is L, and the limit of g of x is also L, this means that the height of the youngest brother approaches L meters, and the height of the eldest brother also approaches L meters. Then, as x approaches c, the limit value of f of x exists, n is equal to L. This means that the height of the middle brother, being sandwiched between the other two, ultimately becomes L meters. Now, let's explore how the squeeze theorem is applied through some examples. Let's find the limit of x squared times sine 1 over x as x approaches 0 in the first example. First, we know that the sine function's ranges between -1 and 1, both inclusive, so we can write sine 1 over x is greater than or equal to -1 and less than or equal to 1. Then, multiplying both sides of the inequality by x squared for all terms, we get x squared times sine 1 over x is greater than or equal to -x squared, and less than or equal to x squared. Now, let's take the limit of all terms. As a result, we can express the limit as x approaches 0 as shown on the screen with inequalities. However, we can easily find that the limit of -x squared as x approaches 0 is 0, and similarly, the limit of x squared is also 0. Since the limit we are looking for is both greater than or equal to 0 and less than or equal to 0, by squeeze theorem, the limit of x squared times sine 1 over x sandwiched between these values is 0. In the second example, we want to find the limit as n approaches the infinity of -1 to the power of n over n factorial using the squeeze theorem. In this problem, we need to find a function that we can compare to n factorial. N factorial is the product of all positive integers from 1 to n, while 2 to the power of n is the result of multiplying 2 by itself n times. When you compare these two operations, we notice that 2 to the power of n involves repeatedly multiplying by 2, while n factorial involves multiplying by increasingly larger numbers. A simple comparison, such as calculating 10 factorial, resulting in a value well over 3 million, while 2 to the power of 10 is just 1024. Therefore, as n approaches the infinity, n factorial will be greater than 2 to the power of n, and the reciprocal of this means that 1 over n factorial is less than 1 over 2 to the power of n. So, -1 to the power of n over n factorial will be greater than -1 over 2 to the power of n, and at the same time, smaller than 1 over 2 to the power of n. Now, if we take the limit of each term in this inequality as n approaches to infinity, it will be expressed as shown on the screen. Now, as n approaches infinity, the limit of -1 over 2 to the power of n on the left-hand side will become 0, because the denominator's value keeps increasing. Similarly, the limit on the right side will also become 0 because the denominator's value increases indefinitely. As a result, the limit of -1 to the power of n over n factorial must lie between 0 and 0. Therefore, the limit of -1 to the power of n over n factorial as n approaches infinity is 0. The square theorem is foundational in various advanced calculus and mathematical analysis topics, including sequences, series, improper intervals, and differential equations. It provides a rigorous way to analyze and understand these topics. If you found today's video helpful, please like and subscribe. Thanks for watching, and I've been your Math Guardian, Alex.